Hi everyone, my name is Michel Habib and I'm excited to talk to you about a passion project I have worked on for the past few weeks. It combines two of my favorite topics, VFX and AI. Imagine this. Imagine providing Houdini artists with a tool that allows them to chat with any AI program about their complex Houdini scenes without describing them for free. You could have a network of 100 interconnected nodes, 20 branches, 10 sticky notes, 5 network boxes, 7 loops, and in less than a fraction of a second, you could chat about it with ChatGPT, Claude, Grok, Gemini, GitHub, Copilot, DeepSeek, or any future AI tool that you can imagine. You could ask them to explain the network for you, document it, visualize it, fix a specific vex triangle, or even suggest a better workflow. Houdini to Chat is a proof of concept for a Houdini digital asset that provides an AI-ready description of your scene. In this video, I'm going to explain how to install it, how to use it, and will present 3 different case studies that will blow your mind away. So, how to install Houdini to Chat HDA? First, you need to go to the GitHub repo for Houdini to Chat, and then you go to releases, look for the latest release. Currently we have version 0.1.0, it's the latest one, actually it's the first one, and go to assets, download the zip file, Houdini to Chat zip file, and I already have it here. There are 2 ways to do that. The first one, you go to, if you are on Windows, you go to documents / Houdini 20.5, which is the latest version of Houdini that I have installed, and I go to the OTLs folder. If it's not created by default, you can create it, and you simply drag and drop your HDA in this folder. This way you will have the HDA available to any Houdini scene that you have on your computer. So open any of our object nodes. You can simply, if you click tab, type Houdini to Chat, you will find in the menu here Houdini to Chat. You can just drop the node and it's ready to go. If you already have Houdini open, then you need to go to Assets and refresh Asset Libraries to make sure that your asset is visible to Houdini. The other way to install that asset just for the current scene, you need to go to Assets, Install Asset Library, and then click this and find whatever you downloaded and decompressed your file. Select it from here and just click Install. So let's check how to use Houdini to Chat digital assets. I have Houdini open here. I have a number of nodes. Let's pick any one of them. Let's say this CGWiki Rubik's Cube node. What this node does is it creates 2 Rubik cubes, and if we click play here, the Rubik cubes are trying to shuffle. There are 2 of them. One of them is shuffling using a wrangle that will calculate the shuffling using a set of random axes and random slicing, and the other shuffle algorithm is using a solver that is doing the shuffling using this vex code. And you will notice that the first one has the colors jumping on each slice, and the other one is more accurate because it will shuffle the colors without jumping. So this is one of the exercises that were on the CGWiki website. So what we're gonna do, we will drop Houdini to Chat node. As you can see, there are not so many nodes named Houdini, just a couple of them, and we are the first one. So we will just drop it there. Looking at the settings, it has so many settings, but the default ones are very good, and you just barely need to click this export to chat button, We only need to know the project location, which is where the file will be saved, the exported file. So if we just click export to chat, you can see here that the file is exported successfully. It took about 100 milliseconds, which is just 1/10 of a second. Okay, and if we look at the file here, so this is where the file is saved. Here's the file. We can look at it quickly. If we open, I have my VS Code open. So here's the file, and now we are looking at the description of the scene that we were looking at, and it has at the top here an example prompt. You are a SideFX Houdini expert and handful assistant looking at setup code representation of Houdini network. Visualize the network. Can you explain the purpose of this network? Can you break it down as smaller logical functions? Think of the animated visual output of each function described. So we're going to take this prompt and go to Cloud, put it in there, Shift Enter, tell it, can you open this in Artifacts? It will look prettier. Of course, we need to attach the file. We will find it, attach it. We have Cloud 3.7 site. We set it to be educational responses for learning. I think it will be very good this way, and hit it, wait for it. We're looking now at Cloud 3.7. It's doing an overview of the network. This network creates an animated Rubik's Cube simulation with two side-by-side cubes that rotate slices randomly over time. The network uses different approaches for each cube. Left cube uses a wrangle node for direct transformation. Right cube uses a solver node for accumulative transformation. The result is two visually identical 3x3x3 Rubik's cubes, each with colored faces that animate by having random slices rotated at random intervals, simulating someone solving or scrambling a Rubik's cube. So you can look at the network structure. It's explaining exactly the nodes. It knows the purpose of each node, what is the visual output of each one. As you can see, the level of detail, and given the first description, the first overview, it sounded very accurate. So we can give it a question. Can you tell us which approach is better and why? When comparing the two approaches used in this Rubik's Cube animation network, both have their strengths, but the solver-based approach is generally considered superior for several important reasons. So it understands that the solver approach is better. The solver maintains a history of all the previous transformations. When each rotation happens, it builds upon the existing orientation, rather than recalculating it from scratch. So, and it goes on and on and on. And it sounds very good to me. So, before moving on with looking at the 3 case studies that we have in this video, I want to talk about the evaluation criteria that we are using. The evaluation criteria is based on the LLM or AI tool ability to recognize the following: understanding the scene representation, like the nodes, the connections, the network structure, the branches coming in and going out, the loops, the network boxes, the sticky notes, the node parameters, their values, the default values, expressions, references, user-defined parameters. We also look at understanding the scene logic, the node's meaning and purpose, the partitioning of the network into meaningful parts, network logic and purpose. Also, we look at visualization, visualizing the output, visualizing the animation, visualizing the geometry, and the third case study that we have is about visualizing geometry. It's a very interesting one. Explaining the scene, suggesting fixes and solutions to requests. Also, we evaluate that the files that we create are working seamlessly across LLMs and AI tools. Try multiple LLMs with the same prompts, try multiple AI tools with the same prompts, get acceptable results with regular and thinking models. Also, for the evaluation, there is one critical point to add here, which is it is possible, since we are using in our case studies scenes that already exist publicly, it is possible that some of these scenes were seen before by LLMs, and the LLMs were trained on these scenes. So we tried as much as possible to strip away identifying information from the scene descriptions. We didn't do that for all of the scenes that we used, but we did that for some of them to make sure that there is no bias in the AI to cheat or know in advance what these networks do. Also, I want to make sure that the correct credit is given to every scene that we are using. So shout out to CGWiki, which is a great resource for Houdini and other 3D packages. Also to Mr. Junichiro Orikawa. He is the master of VFX in Houdini, and I enjoy so much watching his videos. Also to the great and popular channels Intagma and Simple and Procedural. We used scenes from each one of these sources, and I think we better get started. So let's look at the first scene that we have here. Then it's a very simple one. The name is xyzdist demo by CGWiki, and as you see in this GIF, it's simply visualizing a point orbiting around the 3D surface. This is the network structure we'll look at in a moment. It's supposed to be an easy network. It has 26 nodes, 5 sticky nodes, 17 branches, and we did two variations of this network. One of them by having the sticky nodes inside the network, and the other one without the sticky nodes, just to prevent the AI from cheating information from the nodes, and try as much as possible to think hard about what the nodes do and what the different branches do to create this visualization. So for a change, maybe we can use a different AI other than Claude and Gemini, but let's first jump into Houdini and look at this network. So this network is simply doing the following. It has a pig head that is colored randomly. Each one of the faces is colored randomly, and it's transformed in a low-res pig, this node. And at the same time, there is a point that we can move here, and whenever we move this point, it projects a ray on the pig geometry, and it draws this red line, and it draws this sphere. The size of the sphere I think reflects the distance, and the color of the sphere represents the color of the prim or the face that it is going through. And this is determined by this triangle, xyzdist triangle, and this bunch of nodes, they create the sphere, and in the end everything is merged together, the big head from here, and then the sphere from this branch, and the point and the red line, all of them together in this final merge node. So this is what the network is doing. So let's look at our Houdini to chat node. It's on the defaults. Just click export, done. Doesn't take any time. And we're going to open VS Code. Now I have this folder opened. I don't need to load any files anywhere. So I'm gonna just look it up. It's here. So I have this file. What I can do is simply go to GitHub Copilot. I have this installed. It's a free plugin for VS Code. I am subscribed to the I don't know what it's called. It's the Pro version, but it's available for free. Anyone can use it. Let me just say I will take this prompt. There is no animation, so I will skip the last line. I will use the prompt here. Which model should we use? Let's use O3 Mini. So your SideFX Houdini expert is the same exact prompt we used before. Can you explain the purpose of this network and its key components in full details? Can you break it down? So let's try this. And it's processing. There we go. Let me try to make it a little bigger. So the network builds a procedural geometry setup where an orbiting point is created and then snapped to the surface of a target object, here represented by the low-res pig. The process involves computing the closest position on the target by way of distance calculation, then using that information to create visual cues. A wireframe sphere scaled to the computed distance and colored from the target. In parallel, duplicated geometry and merge operations integrate various elements into a final composite output. Wow. So the key components: point creation and transformation. Here you go. Attribute initialization. Here you go. Distance calculation and mapping. Here we go. Visualization via wireframe sphere. Here we go. B-scale. Here we go. Creating connections and visual lines. So this is the create line node and the coloring. Geometry merging and duplication. This is the merge one node. So it's very accurate, breaks down everything, it understands the relations between the nodes, it understands the functions of the nodes. And it gives us a logical outline. Create and animate the point, prepare geometry attributes, compute the closest surface position, visualize proximity with the wireframe sphere, connect and composite the elements, target geometry preparation. So it's really extensive and complete, but it's a simple node. So if we go back to looking at the results, we know that Clothes 3.7 and Gemini 2 Flash, they both give us good results. You're able to give a great description for the scene with or without the hints on the sticky notes. Claude's output is much better than Gemini's, and also O3 Mini, now it also has a great output as well. So this is it. So now let's look at a very interesting example. This one is an 8 puzzle game, and if we hit play, look at this. So this is a popular children game many years ago, and the way this network is set up is very interesting. It looks simple, it's like only 10 nodes. So it starts with a grid 3x3, and it has a mandrel picture on it, and the group 0, which is the first face of these 9 faces, is colored in red. And then there's this assemble node. What the assemble node does, if we look at the grid and check the geometry spreadsheet, it has 16 points, which are the different points of the grid. But when we do an assemble, it will pack the grid into 9 squares. It breaks it into 9 pieces. And this is the tricky part. This is one of the tricky parts of that network. Then it calculates the rest position for each square, I guess. And then this wrangle, it starts with a square, and it calculates it gets a random square, and then it tells you what are the neighboring squares around it. And then there is a solver that will simply every single second will switch this empty square with one of the squares around it, giving us this animation of that puzzle. And to give us the illusion that these squares are moving this way, it will blast group 0, which is the first ever red square at the beginning. So this is the network that we have. So let's drop Houdini to chat, export to chat, and if I have the plus version, but this will work even with the free version, and need to upload, and this is the right file. We need to put a prompt, put it in here. There is no canvas mode in O3 Mini, so let's try it. Let it reason, think. Okay, we're looking at the thinking. It's looking at the different nodes. It's trying to break it down into small. Oh, okay, it reasoned for 21 seconds, and then it returned with this. So node, grid node, 3x3, texture mapping, the mandrel, it gets it. Geometry cleanup, the fuse node, okay. Coloring of the group 0, okay. Geometry packing with the assemble node, and it continues on and on and on. So let's see if it got the animation right. So the entire network is designed to create a dynamic animated grid where points snap to calculated positions at periodic intervals, then smoothly transition between these states. So somehow it doesn't get exactly how the effect is working. So what it missed so far is the assemble node. It doesn't understand exactly what it does. Also, it doesn't understand that the blast node will remove one of the squares. So let me try to give it a couple of hints. Okay, so I need to give you a couple of hints. The assemble one node will convert the grid into 9 packed squares. You can check what assemble node does to achieve that. The second hint, the blast node deletes one of the squares, 0, which is the one colored red. It's a square, not a point, since it's a packed primitive. Can you reimagine again using this info? Let's see. So it's reasoning. Okay. So it understands now a little bit. So final visual and purpose. A 3 by 3 grid initially composed of 9 squares is transformed so that one red square is deleted. The remaining squares animate by snapping to grid positions and interpolating between the movements, creating an engaging dynamic pattern with an intentional void. The network demonstrates how to procedurally group geometry into larger packed primitives, mark and remove specific elements, and so on, so on, so on, so. Okay. Can you name that game? Misho, that's me. With the grid split into 9 squares and the red 0 square removed, the network is essentially recreating the classic 8 puzzle. Yes! A sliding tile puzzle where you maneuver 8 tiles around an empty space. Very good. Very good. So let's look at the last one, procedural burger. So this one is building a procedural components of a delicious burger and simulate them falling down. This is a very hard one because it has so many nodes, and you can see the simulation here in this photo. But what's interesting in this one is we're not gonna ask him a lot about the process of the network, but we're gonna ask him about what it looks like. Let's look at the Houdini scene so that you can understand what I'm saying. So we are looking now at the network. We have 7 different network boxes. Each one of them represents a part of the burger. So this net 1 is the bottom bun, net 2 is the patty, the third net is the cheese, next is bacon, next is pickles, next is the upper bun, and then we have a network that has the sesame on top of it. I have this quick photo, this one. So each one of these null nodes should be representing one component of the burger, and it's fully created in a procedural way. What we did here is we removed every trace that says this is a burger. So we had group names for each one of these components, we changed them, and we have nodes with the burger name, we renamed them to secret, out secret node. So this is the goal for the LLM, is to figure out from looking at these procedural, very procedural nodes, what they actually represent, each one of them. There are 7 networks, all of them grouped together into one single burger. So let's start by adding Houdini to chat. Note, what we need to do, we want to export all of these network boxes into a single file. So we will simply uncheck that option. That creates a separate file for each network box. So now we will have, when we export to chat, we will have only a single file. So if you look at it here, it has all of the boxes, and if you look at the group names, all of them are renamed. There is nothing here that mentions that this is a burger. So we go back, let's say, to close. So we're gonna put the prompt, and we're going to pick the secret object, and we will ask to imagine the different shapes in each out node that are merged together into an out secret node at the end. And let's go. So we can see 9 different networks, 7 separate networks that each create different geometric components, a merge network that combines all of these components, a simulation network that applies closed physics to the merged object. That's excellent. So network 1, circular base component. Okay. If we bring up a photo, we can visualize this a little bit. So what appears to be a circular disk with details. Okay. Smooth surfacing. A circular, slightly organic looking textured disk with beveled edges and a warm golden color. That's the lower one. And then a larger, I don't know why it says larger, but it says larger circular base component colored in brown, so we can recognize the color. Okay, positioned to align with the first component. And then a flat grid component with smooth edges and the bright gold color. That's the cheese. Doesn't know cheese yet. And then organic patch shapes. This is the bacon. Uses a planar patch and places copies on points scattered on a box. Several organic, slightly curved surfaces resembling petals or leaves arranged randomly in space. Colored red. So it's trying to guess what they are, but it doesn't know yet. And then 5 tubular elements. Multiple cylindrical tubular shapes arranged in space with varied orientations. Colored green. These are the pickles. It doesn't know it's pickles, but it can guess, it can visualize how they look like. Next, complex circular component. It says complex. Multi-layered circular object with progressive smaller rings stacked together. So it doesn't know exactly what this is, but it knows it's warm gold. And then network 7, scattered points on a sphere. This is the sesame. An ellipsoid sphere with numerous small elements scattered across its surface in varying peachy orange hues. And then the merge, and then the simulation. We are not interested in simulation right now. So the final result is a complex sculptural object created from various geometric components. It doesn't try to suggest an object. So we are going to give him a second question. So this is my second prompt. I believe if you can guess it. I believe you can guess it if you think harder. Think about objects 1 to 7, their shapes, their colors, their relative sizes, their possible relative positions, and you can guess this organic item correctly and its individual elements too. So, looking more carefully, I'm now realizing this is likely modeling an organic food item. What? Let me reconsider each element with this in mind. When I examine the color schemes, shapes, relative positions, and the physics simulation that makes everything settle, I believe this is modeling a hamburger or sandwich. Let me break down the components. Let me bring up the photo. This is gonna be interesting right now. So, network 1, classic light golden brown bread color. This is the bottom bun of the burger, correct? Network 2, this appears to be the burger patty itself, correct? Properly sized to extend slightly beyond the bun, that's not correct, but doesn't matter. And colored in a cooked brown meat tone, absolutely. Network 3, a flat grid platform colored brightly yellow, gold. This represents a slice of cheese on the burger, of course, American cheese. What else? With that distinctive yellow color. Network 4, organic patch shapes. These are tomato slices, absolutely wrong, with their characteristic red color and organic curved shapes. Network 5, tubular elements colored green. These represent pickle slices or possibly chopped lettuce pieces. Pickle slices it is. Network 6, multi-layered circular components with golden color. This is the top bun of a burger, which often has more complex shaping, and so on. So, network 7, these could represent sesame seeds on the top bun. Unbelievable. Or possibly other small toppings like minced onions. This is insane. This is absolutely insane. Claude 3.7 could guess exactly that this is a hamburger. It knows exactly each one of the components here. Maybe it missed one, but that's fine. Come on. And it's really amazing. It's really amazing how it can visualize how the different elements are progressing in the network to become this object. This is really crazy. If we actually go back to the evaluation, I already ran these tests before, so I got the same results for Claude. Actually, for Claude, it still recognized the network 4 as tomato slices, but it guessed everything else correctly. O3 Mini, it guessed 6 out of 7 elements correctly, but it didn't know it's a hamburger. And Grok 3 could guess 3 out of 7. It was the lowest rate for Grok 3 on this specific test. However, the results here are really unbelievable. Thank you everyone for watching. I hope you are excited as I am about completing this project. If you find it useful, let me know. If you have questions, let me know. If you have issues working with it, ideas to improve it, I am waiting to hear from you. Your feedback is very important to me to decide what to do next with this project. See you soon. Bye.